All right, let's talk about the skydriver problem. It's the drag forces. All right, and here it is. Here it is. What happens? Here's what happens. I'll show you what happens. Here's the skydiver. So besides just getting the answer, so you can move on with your homework, let's actually see what happens. All right. First of all, when they're going to be coming down in a pike position, so I guess the pike position is their head kind of with their neck here, their arms like this, straight back, and their feet straight back. That's kind of the pike position, and they're going to be flying down. Now, here's what happens. Here's what happens. Or maybe they'll be the pike position might be they're completely flattened out. Okay, so they're flattened out, and they're coming and they're hurtling down through the air. Well, eventually what happens is you get all these air molecules. So if you're coming down head first like this, there's not a whole lot of air resistance there, because look, this isn't so much space, but this causes more. Either one, both of them, this happens. You get a bunch of air molecules start to accumulate under here. Start to accumulate, build up as you're plowing through the air. It's just like imagine. I know we used to shovel snow around here. Told you today. I should have stayed in frickin' bed. Anyway, we used to shovel snow here in Missouri, but those days are kind of gone a little bit. I'm hoping they come back someday. I like, but anyway, when you shovel snow, what happens is you're pushing the snow along. If you're plowing it, they're plowing. A bunch of snow collects in front of your shovel until eventually you got to kind of throw it out of the way so you get some more. Well, if you never throw it out of the way, you get this huge mound of snow in front of your thing. That's what happens here. And what happens when you're pushing that along? You get slower and slower and slower. All right. And so eventually what happens is you get a lift force or a drag. Let's call it the drag force. But no, it's not RuPaul. But anyway, okay. So, who I think is hilarious. I think he's great. But anyway, so you get this drag force. It's F of D. And let's see what the book says is the formula for that. The force of drag, F of D, is equal to 1/2. There's a drag coefficient that everything has. So there's a drag, C. And then this rho here is air resistance. A is the area, is in square meters of the body falling. And V squared is that terminal velocity. We have to calculate what their terminal velocity is. Okay, we're going to notice in here, there is no mass. There's no mass here. It all has to do with those air bubbles. The mass is kind of covered here in the row. I never thought of that before. But that's where the mass, because I just have blindly been writing down this equation. Now I see where it comes from. So let's do this. Let's write down the equation. Here's the drag force, FD. Okay. C, drag coefficient. Because I'm going to give you a question off this on the exam, because I think this is cool stuff. This is like real world things. Times rho. Rho for our purposes, we're going to go with 1.21 meters cubed, or kilograms cubed per meters cubed, or kilograms per meters cubed. Gosh dang, I forgot what density is. This is your air density. Okay, that's your air density. Area, cross-sectional area of the body. And let's use 0.14 meters squared for this problem. Okay, let's use area as 0.14 meters squared. And then, so it's coming down, and then the terminal velocity squared, which we need to calculate. Okay, and we're going to say they get to the terminal velocity. We're going to say at 6,000 meters is when they reach the terminal velocity. And I think for giggles on Tuesday, I'm going to show you like a 4 or 5 minute Stratos video, which is really kind of cool, of when Felix Baumgartner jumped. I mean, I know there's a lot of equipment, but that was a space age type thing that he did. I mean, for a private, I mean, it was a big advertising campaign for um, uh, Red Bull, but it's whatever. Okay, it's still cool. Is A times V squared. Okay, so there's the drag force. All right. All right. So now, how do we calculate that velocity? Well, let's look at the free body diagram. Drag force going up, gravitational force going down. I want a terminal velocity. That doesn't mean it's dying. That means it's not getting any faster and it's not getting any slower. Terminal velocity always also means a constant velocity. When we have a constant velocity, what the heck is our acceleration? 0, dog. That's right. Okay? So that's how that works. So you said this guy equal to this guy. And what's the force due to gravity? This is mg. So you're going to have different terminal velocities for those guys due to drag. Due to the drag, you're going to have different terminal velocities. So things that are bigger fall faster in the air. On the moon, not the case. Not at all. Okay? As a fact, I got to show you that video too of dropping the hammer and the feather on the moon. All right. So basically, what you do is you go, okay, well, mg is equal to 1/2 c rho a v squared. Now you might be going, well, what the hell is c? I'm going to tell you in 1 second. Did it tell us what c is? Oh, here's for him. What about for a skydiver? Right here it is. Skydiver 1.0. We're going to go with his. We're going to go with the skydiver's 1.0. Or is the pike position? I'm going to assume that the pike position is head first, or is horizontal to the thing. Okay. Whereas notice, skydiver feet first, there's less air to collecting. All right. So we'll finish the skydiver problem in the next video because I had to teach it. Then we had to. Now we'll do it. Now we'll look at it because I think we got drag coefficient. We're going to say is 1. Oh, no, let's go ahead and finish it. I just had to do that real quick. So up here, the drag coefficient is equal to 1.0. All right. So you've got each skydiver's mg. So you're going to have to compute for each one. Cp times A we were going to say is 0.14 meters per second squared, v squared. So each skydiver, see, notice if he's got more mass, he's going to have a higher velocity. Except that if he has more mass, he might have more body area too, which might negate that. In other words, if you got a huge area, look what happens when you compute for velocity. This huge area is going to make this number kind of small. It's going to cut it way back. And as a matter of fact, that's what a canopy does. That's what a parachute canopy does. It makes this area huge. And so your terminal velocity is pretty small. I just thought of that. I didn't think of that before. All right, well, let's take a look at this problem some more.